Good afternoon, ladies and gentlemen. Thank you for attending this webinar. The topic today is concrete rib design in SCIA Engineer version 22. My name is Tomáš Pajl and I'm product owner responsible for concrete design domain within SCIA Engineer. Before we start, actually, just information that you are muted during the webinar, but do not hesitate, please, to ask questions in the GoToWebinar question box. Today with me are three colleagues, Lukáš Dlouhý, Pavel Valach, and Jakub Kršík. We'll be more than happy to answer your questions. Also, we will send you all the materials which will be used during the webinar, mainly the ESA file with the project. And the recording will be available on our YouTube channel in a couple of days. So it will be possible to watch the webinar again in future. What is today's agenda? Quite simple topic in terms of explanation, because concrete ribs are very frequent structural members in multi-story buildings. And if we speak about SCIA Engineer and how we can deal with concrete ribs from the modeling perspective, there's no big secret, because mostly we model the concrete rib as a two components, 2D plate. We've connected 1D member on some eccentricity to simulate the web or the rib itself. Yeah. So from the stiffness point of view, it's no problematic solution, because actually we do not duplicate any stiffness. So we actually get the deformation which is common for the slab and for the rib part. And we can get the results of the finite element model, which actually correspond with the reality. Yeah. Different topic actually is the design of this concrete rib, because basically with this system of two components, we need to merge them together to get overall section T or L, and we would like to handle these ribs as a 1D object, so we can use the beam theory for the design and checking of the reinforcement. So basically what we need is to transfer the internal forces from the beam and from the slab and get the design forces on the overall section. And we also need to compose the section also to be able to design the reinforcement. So two big tasks, and the common for both is we will handle part of the slab using the effective width. This effective width can be different for forces and for cross-section design, and how to find the proper effective width. It will be the main goal of this webinar. Basically, if we speak about SCIA Engineer, we are able to handle concrete ribs actually in three different ways. Common for all of them is that at the beginning we have the 2D plate and beam on eccentricity, and we can integrate internal forces using concrete rib as a structure element, but we can also input on the structure integration member or integration strip to get the design forces. Yeah. For concrete rib and integration member, we can even go further and run, for instance, reinforcement design or even make the code checking. So it's not necessary always to work with the concrete ribs, because you can see that, for instance, using integration member, we can also play with the user-defined eccentricity of the beam. We can keep the FEM results after any change of the effective width, etc. Yeah. So to demonstrate those three options, I will use this very simple model with plate of thickness 200 millimeters. Ribs will be all with same cross section 200 to 150. So the eccentricity will be actually 300. And to make it as simple as possible, we will just use one load case with surface load whole slab with 6 kilonewton per square meter. So now I switch or jump to SCIA Engineer and just simulate all three options to actually first get the design forces. Yeah. So first I will start with the rib, which is actually the most frequent option. So just type rib, select this command. It's asked to select the plate. After confirmation of this dialog, I can model the rib from one support to another. And now I'm modeling it as a two-span rib, and for each span I have a single member. Yeah. After confirmation, I can immediately calculate effective width automatically, and basically I could run the renal analysis and get the results. Yeah. But before that, I will also do another option, which is that I will just model 1D member. This 1D member, I'm using same cross section, but this time I will input some eccentricity to get the same shape like the rib previously. And again, I can get quickly the rib modeled, but now as a beam on eccentricity. Yeah. This model would not work actually because still I have not linked the beam on eccentricity with the slab, while in the rib it's done automatically. So what I have to do is that I need to also model internal edge. Select again the slab and input the internal edge actually on the same position like is the system length of the beam. Yeah? And just because of this step, automatically is linked the beam on eccentricity with the slab because they have same plane. Okay, so now I can calculate the results and just quickly check whether, for instance, my deformation is what I would expect. Yeah. So, for instance, I can select just those two new ribs or continuous ribs and go to the 3D deformations. And for my load case, I can display the deformation. Yeah? And you can see that actually I have same deformed shape of both options. So basically, this is what I need. I have confirmation that I have connected 1D beam with slab for both options. Yeah. Now what I can do is to get some results of internal forces. So what I can do is now go to the internal forces command, the basic one, and again select the concrete rib and beam on eccentricity. And first I will use the option without this option rib and display the bending moments. If I do that, you can see that I have quite small effort on the beam on eccentricity. But now if I click and tick this rib option, I immediately see the difference between both options. Yeah? And the reason is that actually within this effective width, I'm now integrating the internal forces also from the slab. and forces from the beam on eccentricity and from the slab I'm integrating on the overall section with new center of gravity. Okay? Now I can do the same also for this beam on eccentricity, and I'm using another feature of SCIA Engineer, and this is, for instance, integration strip. So again, I just need to select the slab. I need to have the same effective width as is used in the concrete rib. So it's 2612 millimeters. And I'm using this option for the first span. And for another span, I'm using another way how to get the results, and this is the integration member. Again, it's a little bit different way how to define the effective width, but you can see I am defining the bounding box left and right, and for bottom and top, it's not necessary to input big value because for me it's necessary to just cover the central plane of the 2D slab. Yeah. Okay, so just quickly model also for the second span, and now I can get actually the results for both options in terms of concrete rib. Yeah. What I have to do is just go to the internal forces, and now I need to take another option in the result service, and this is the integration strip / member option. Yeah. If I have this option ticked, now you can see that I have the results almost same. Yeah. So for the integration member, what I just need is to little bit increase precision. So I will increase the number of sections. Yeah. If I just now focus on this first span and refresh the results, you can see that I'm now on the same, absolutely same internal forces. Okay, just quick note about the integration member. You can see that here is options actually to integrate the internal forces. First is center of gravity, which actually do or does what we want, yeah, to make the cross section of the rib, because the integration member is able to identify the slab and the beam on the eccentricity, create the common cross section, and integrate the forces to the center of the gravity of the integrated elements. But there is also another option, definition axis, which actually would lead to different results. So just quickly show what I mean by that. But in this case, actually, I'm integrating not to the center of the gravity, but actually I'm integrating on the position where I inputted the integration member. Yeah. So just I will run the drawing tool, and we are now here. Yeah. So that's the reason why I have different internal forces. In this case, it's just minor change, but if the eccentricity between the center of gravity and between the definition axis or the distance is significant, then the difference can be also significant. Yeah? So I will just input it back, this option, and basically refresh the results to get what we want. Yeah. Now I jump back to the presentation and quickly explain what's actually going on. So we have actually tasked to integrate the forces from the slab and from the beam to the common position. Yeah. What we can do is that we can get the internal forces from the slab in terms of normal force and the bending moment. We can get the same from the beam. It's important to notice that for the beam, it's independent on the effective width because still on the beam I have the same amount of internal forces. What is only changing is the internal forces which are integrated from the slab based on the effective width. Yeah. So for this arrangement, actually I'm getting these forces, and it's important that if I, for instance, sum up the force, normal force or axial force from the slab and from the beam, I can see the difference, and this difference is the actually axial force in the rib itself. Okay? And if I sum up the bending moments from the slab and from the beam, I get the moment, but it's not actually still the moment which is in the rib, because I need to take into account also the eccentricity of the axial force in the slab and in the beam to actually calculate the additional bending moment because of this eccentricity. Okay? So what is the result is that my bending moment M rib is composition of this bending moment from the beam and plate, and also multiplication of axial force from the plate on some eccentricity and beam on another eccentricity. Okay, and problem is that quite often we don't want to design actually the concrete rib just on the moment and not as a combination of moment plus normal force. Yeah. So actually, what we can do with that, I will jump back to the SCIA Engineer and explain several possibilities. Yeah. To actually get the internal forces, which probably might be the best in terms of effective width, I just created the simple model next to this what we are using, and actually loaded this frame as a line load, which is actually this surface load on this span of six meters. Yeah? And then if I compare the results, for instance, for this first span in terms of internal forces, I can see that I have significant difference in bending moments. Yeah? And I'm also getting this axial force in the rib, which actually in the T-beam model is not presented, but actually in the concrete rib is quite often there. Yeah? Why is that? Again, if I go to presentation, the reason is that actually we integrate just this part of the axial loading of the slab, but actually we still miss this part, which is still contributing to the overall load bearing of the concrete rib. Yeah. So actually, if we put together the force in the rib, force in the plate, in the beam, we have actually the equilibrium. But when the equilibrium is not present there, then always we have this normal force. Yeah. What we can do is simple step. We can increase the effective width. Yeah. But before that, just I show you also the impact on internal reinforcement design. So for both options, concrete rib, integration member as a rib, I can continue not just with the design forces, but also with the reinforcement design. What I have to do just to activate the command for the reinforcement design, and maybe before that, just check what are my design assumptions, which is common because it's for beam and for the rib. So I have diameter 12 as a design diameter. I'm now just using the required reinforcement design, not the provided one, and use a cover 30 millimeters. Okay. What is also essential is to check the internal forces. where actually for the beam, which will be used for the integration member, there will be just uniaxial loading, but including the normal force. And for the rib, we have actually the same setup. Yeah. Okay, so now I can just run the design and see the impact on a required reinforcement area for all three options. Yeah. So now you can see that I have for the T-beam option 465 square millimeters, but for the option with combination of normal force and bending moment, I have smaller amount of required reinforcement area. Okay. I can also check the results in detail to, for instance, confirm whether I'm designing including the normal force. So I just display the output for the rib. You can see that there is what is expected normal force and bending moment. If I check the T-beam model, I'm getting actually the required reinforcement area only for the bending moment because normal force is 0. Okay, so now what I can do is to try to find the effective width where the normal force will be actually the 0 within the rib, and I should get actually the same internal forces like for the T-beam. For the integration member, it's quite easy because I just need to change the effective width to 5 meters. You can see that still I have available results from the finite element analysis. And now I'm running the command to get the design bending moment for both options. And you can see that now I'm quite close to the bending moment from the T-beam model. And if I check the normal force, you can see that still is there, but now the value is very, very low. Yeah. What's important that if I have changed actually the integration member width or the concrete rib width, still I'm designing on the cross-section which corresponding to the original cross-section with the effective width 2612 millimeters of the width. Yeah. So then what I can do is to compare also the design results in terms of required reinforcement area. So just calculate the design again, and you can see that now I'm getting almost same results for the positive bending moment, but for the negative bending moment, actually I'm getting the higher value. And the reason is that actually for this concrete rib, I'm using constant effective width. And it's not correct in terms of integration of internal forces, because if now I go to the, for instance, these results of 2D slab and display the basic results of internal forces of 2D slab and check, for instance, the normal force in the slab, which is parallel with the rib. Yeah. You will see that the distribution actually of the results is not constant actually, but it's always concentrated in the area of the support, and actually for each section in either scenario we would need actually the different effective width. Yeah, based on the code, it's not necessary, but it's necessary to find the effective width which somehow have reached all these differences along the concrete rib. Yeah? It's also visible in terms of if I display the results on the section, where you can see that actually distribution of the axial force in the slab within the effective width is not constant, but actually there is peak above the rib, and then the distribution is or the load bearing is lower and lower. Okay. So first option is actually to increase the effective width of the concrete rib. If I would do the same, for instance, for the rib which is modeled as a rib, yeah, I can do it as well, but now it's a little bit more complicated because I need to switch from the automatic calculation to the manual one, and I can input the internal force, the integration. Sorry. Sorry for that. I input the width of 5 meters for integration of internal forces, but for the checks, so for definition of the cross section, I'm still using the original effective width. Yeah. Now you can see that the results are deleted of the finite element model, so I need to recalculate the analysis. But again, now I should get the reinforcement design, which is actually the same for all three options. Yeah. But this kind of solution probably is only for the case where we would like to design these ribs without design of the slab afterwards. So now we assume that all the loading actually is transferred by the rib. So actually we will now design only the rib. Yeah? Now I will just show you also what may happen if I increase even more the effective width, for instance, to have the size of half of the span on each side. Yeah? Now if I rerun the design, you will now see that now the integration of the internal forces is even bigger than the reality, because you can see that now I have increased required reinforcement area, and now if I'm going to display also the, for instance, the normal force, you will see that now I'm having no tensile force in the rib, but the opposite actually, which is the compressive force, which indicates actually that I'm integrated from the slab much more than is actually transferred by the rib. Yeah. So you can see that the ideal effective width for this scenario was this 2.5. Yeah. Now let's go back to the situation where we will have the effective which is automatically calculated according to the code. And now I need to do that also for this concrete rib, because there is another option how we can deal with this normal force. and it's automatic recalculation of this normal force to additional bending moment. Yeah. So let's a little bit wait, and this option is available only for the rib. So if I'm now select the rib and go to concrete data, here I have possibility to actually disable the axial force, but calculate the recalculation of the positive bending moment to additional normal force. What this option is about, it's just simple strategy that we have some normal force in the rib. It indicates that in the beam it's much more effort because there is tensile force. So we just first make the equilibrium of the normal forces. And it means that actually we put the normal force of the rib on the position of the slab, centroidal plane. But because the center of gravity of the T section or the rib section in general is the different position, we have again the eccentricity. And if we multiply this normal force in the rib by this eccentricity, we have additional bending moment, which is calculated by this formula. So let's see what is the impact. So here I have option which actually is that I also here can deactivate the normal force, but here you can see that I have no option to activate the recalculation of the normal force to additional bending moment. So now I will have nice 3 examples which we can compare together. So let's start directly with the reinforcement design and see the impact of this setting on the design efforts. And you can see that if I just neglect the normal force, calculate only on the bending moment, I have 390 square millimeters. If I recalculate the normal force to additional bending moment, I have 402, and the T-beam option 465. Yeah. So you can see that actually the impact in this scenario is not so significant, but it's fully okay, because if we use this effective width, probably we assume that for the rib, we will design the rib only for this effective width, but between the ribs, actually we will design the slab on the effort which is there. Yeah? What I mean by that, again, what I can do is to go to the internal forces of 2D, yeah? And display first results on the section of the normal force. So what we actually did by the step of recalculation the normal force, that we somehow simulate that this load is missing, and we somehow cover it by the additional moment. Yeah? But what we still haven't covered yet is if I display the bending moments parallel with the rib, you can see that, maybe I will rotate, that we integrate the moments in this area, but still we are missing integration of the moments here, which if we would do that, actually it would lead to the same results like for the T-beam model. Yeah? But okay, because in terms of design, we have option to display the forces only in the part, on the part of the slab where the rib is not applied. So if I now select this option rib, yeah, and display the results, you can see that now actually from the perspective of slab, I'm designing only slab outside of the effective width, because there I assume that the load transfer is done by the slab, but for the effective width part, I'm designing it as a 1D. Yeah? You can see that this option perfectly works for the RIP option. Yeah? But if we look on the integration member story, you can see that this option is not working when for the RIP or when we simulate the RIP through the integration member. So be careful about that. And of course, we can now continue and, for instance, go to the design of the reinforcement on the slab. So I just select the slab. I select the lower reinforcement in the direction parallel with the RIP. Again, I have activated this RIP option to just design outside of the RIP. And then actually it's perfectly okay to neglect some loading from the T-beam approach, because I'm expecting that next step after design of the RIP would be to design the reinforcement within the slab, but outside of the effective width. Yeah? If this option is not activated, again, we can compare the results, and you will see that actually after that I have duplicity, because I will design the reinforcement within the effective by 1D, but also by 2D. Yeah? So for instance, be careful in CDD when you would use, for instance, the required reinforcement option as an input, because then you can have the reinforcement twice there. Yeah? Okay, and now it's time to show you that probably it's not necessary to think about effective width for integration of internal forces, because if we have this recalculation to the additional bending moment, and we assume that outside we will design the slab, then we are quite safe. I will show you what I mean by that, because now I will simulate the situation when the effective width will be really small. Yeah? So for instance, just 500, yeah? And keep the section for the design in original shape. And I will do that also for the integration member, and you will see the big difference. Yeah? So still I'm recalculating the normal force for the RIP, but for the integration member I'm just simply neglected that. Yeah? Okay, so I will recalculate the model once more. And just check this, not real example, but I would like to show it for demonstration. That actually the calculation of this normal force is quite powerful. Yeah? So you can see that now the difference is quite significant. So I have 240, 353. So you can see that it has some big impact. And of course, then it's up to you to say, okay, rest I will design as a slab option to just concentrate the reinforcement, for instance, into the rib, or you can also use another approach like to increase the effective width to actually cover the load bearing completely by the rib. Yeah. Now there is one big important thing. You can see that actually the normal force which is in the tension, maybe I will also display the internal forces, is recalculated. Yeah. So I'm now showing the normal force. You can see that originally there was about 50, but because of the much more effective width, now I have significantly increased the axial force because there is big disbalance between what is integrated from the slab and what is actually transferred by the rib. But you can see that I have also compression force. Yeah? And if I now display the design normal force, you can see it will be 0 everywhere. Yeah? But if I display the design results, you can see that actually the reinforcement area is not changed. So it's very important to understand that currently is recalculated only the positive normal force in tension, but not in compression. Yeah? So if I display the bending moments, you can see that there is discrepancy for positive bending moment, but negative is the same. Yeah? And also I can display it as a comparison between original normal for bending moment and the recalculated, which for the negative bending moment is not touched at all. Yeah? But it's simple actually to improve that, and because now I would like to show you what we can do, and just let us know whether it's good approach to also recalculate the negative bending moment, the compression force within the effective width on the bending moment or not, because now I changed actually the method. Yeah? And now if I calculate the bending moment, you can see that also for the axial compressive force I have increased bending moment. Yeah? Why we neglect it now is actually that we assume that for this area actually the reality is that the effective width should be much smaller, and also the design effort of the rib is smaller than comparing to the effective width size. On the other hand, if you compare then the design moments, for instance, for this beam model, then there is a really big difference between 146 and the original value from the beam solution 212. Yeah. So to check the results and trust to the solution, it might be better to have it. And of course, mostly for this situation, it will have also direct impact on the reinforcement design, because now if I run the reinforcement design, sorry, I need to recalculate it. Because the results are still stored. you will see that I will also increase the negative reinforcement area or the reinforcement area for upper surface. Yeah. So you can see that even with when the effective width is not correct, but you have activated recalculation of the normal force to the bending moment, you can get some kind of safe results. Yeah. Now what I can do is just to also calculate the design on the integration member with the axial force. Yeah. So we completely neglected in the previous scenario, but just to show you also a situation where the axial force is just taken as it is. We will see again some interesting results. And now you can see the problem that actually with the taking into account this normal force, actually probably we are okay in terms of positive bending moment, but above the support the situation is absolutely not okay. So question also is whether this recalculation of the normal force should not be the default or not for the rib. So again, let us know, because it's for us very important feedback. So some summary. So for this part, so it's very important that there is big difference whether you take into account the normal force or not. So here you can see the design with normal force, without normal force, and probably also with the correct effective width when we expect complete transfer of the load by the rib. Yeah? We can play with the effective width for internal forces for both options, integration member as well as the concrete rib. We can recalculate the tensile force now on the additional bending moment. It's question whether we should do it also for the compressive axial force. And this actually step prevent us to design the rib always from the safe perspective, because you see that when the effective is wrong and we calculate the reinforcement design on combination normal force and then bending moment, we can get also problems. So the solution to always take into account normal force and bending moment might not be also the solution in all cases. Yeah? And it's important that when we assume that part of the load is transferred by the rib and part of the load is transferred by the slab, we should design both, but with the option that for the 2D design we neglect the internal forces within the effective width of the rib. Okay. Now there is also topic of the effective width for the design or check of the cross section. You can see that basically from the distribution of the stress point of view, we have not constant distribution of the axial stress, but in reality, we would like to use the beam theory. We need the constant stress and also constant compression zone. And now you can see why actually the effective width is, for instance, not bigger, because actually we try to this non-constant stresses somehow simplified to constant stress profile over the effective width. Also, that's the reason why there is a lot of inputs related to how the effective width is calculated according to the code. We fully support the automatic calculation by the code, but there is very important to think about few aspects. Yeah, the first aspect is the detection of the spans, which is based on the buckling system, and based on the spans, actually we can calculate this effective spans and calculate the effective width. And it's also important to think about detection of adjacent members, where we detect the parallel beams with some tolerance. It's also considered the plate edges, but always it's considered as a free. I will show it later. And also it's important that the openings are also taken into account. Yeah. So very quickly, what I mean by that is now I will delete all this beam on eccentricities, and I will input quickly the RIP to have the symmetricity to compare the solutions. Yeah. So first, what I will change is that now I will not model the RIP as a member per span, but I will input the member as a continuous RIP. Yeah. So here I just also enable the automatic calculation of the effective width. Yeah. And if I run the calculation of the effective width, you can see that actually the effective width for the option of continuous RIP is different than the option for the situation when there is a member per span. Yeah? If I display the buckling system and system length, you can see actually what or actually how the spans are detected. So here you can see that it's fully okay because the support is respected, and I have two spans in this scenario. In this situation, you can see that I will have probably only single span as a simple beam. Yeah? So then definitely I have different effective length. Yeah? What I can do is to try to connect, for instance, the continuous RIP with this point. Yeah? So for instance, I can do connect members and nodes. I select this node and this RIP. Okay. Probably I will have different buckling system. You can see how I have the same scenario like the next RIP. But if I calculate effective width, you can see there is no difference. Yeah. And the reason is that in SCIA now we support just one span per member, so we cannot actually compare two effective widths for one member. Yeah? Also, it's important that you can play with that even more. So, for instance, now I will input the series of RIPs, yeah, as it's recommended. So one per span, yeah. Okay. Now if I check, maybe I now recalculate the effective width. So you can see probably I have correct differentiation between the end span and the middle span. Here you can see there is also opening which is respected. But if I go to the backlink data, I can say that, okay, for those two ribs, I will assume only one span. Yeah. So actually, I can do some arrangement, save this situation, and recalculate the effective width. And you can see there is information that now my spans are not in the proper ratio like it's recommended by the code, but okay, I can continue, and you can see that now I have the effective width much bigger. It's also important that I will now delete those two ribs and model them in different way. Yeah. So I select the slab. Now I'm defining the rib from the left to right, but the second one from the right to the left. Yeah. So actually I have different coordination system. Yeah. And now if I select this rib and display the buckling system, you can see that I have only the simple beam because actually there is discontinuity with the LCS, which also means that there is a discontinuity in the buckling system. Yeah? So solution is just to I don't know now where it is. If I reverse orientation, this one is wrong. So now I have both ribs in the same way. I will display the buckling system, and now I have again the correct detection of the spans. Yeah? Okay, and last what I would like to show you is the situation where I have this rib and I would like to, for instance, replace this L rib by the support, for instance. Yeah. So what I can do is to delete the rib and input the support. Yeah. Support onto the edge. So actually, I assume there is support. It can be also wall, whatever. But if now I select the rib and calculate the effective width, you can see that now I have difference on the right side. Actually, right and left means if I watch against the axial force. So this is the right and this is the left, and you can see that there is support, but it's not considered, and actually this edge of the plate is considered as a free and not as a supported. Yeah? So be careful also about this fact. Sometimes it's also it may happen that the support by the wall is not properly recognized, so you need to change the buckling system to fix it. Yeah? So basically, the goal is to have the effective width which somehow correspond to the situation when we have the averaged the stress distribution, and I showed you what aspects you need to consider to use the automatic calculation of the effective width. Yeah. So as a default, the effective width is same for the internal forces and for the checks. But of course, what you can do is to change it. Yeah. So for instance, you want to design just reinforcement for the web part, yeah? But with the integration from the complete effective width, and we just calculate the FEM analysis, because again we changed the RIP property, which basically does not have any influence on the finite element calculation, but it's as it is. And now if I go to the design and design the reinforcement for this option, you will see that I'm able to design also for different cross sections than is used for calculation of internal forces. Yeah. So now it's just a rectangle shape. Yeah. Okay. Of course, what you can do is to continue with the design in terms of to activate the template for the provided reinforcement, input some assumptions about the real bars. Check the provided reinforcement. Also see what is the utilization of the provided reinforcement to quickly see whether everything is okay or not. And if yes, then convert the reinforcement to real bars. And for instance, run the overall check for these options. Yeah. So quickly check whether the design is okay or not. Yeah. So here it's not, but now I will not investigate it more. And actually, then I can do also last step, which is very important, and this is that I can even use the reinforcement from the RIP in the calculation of codependent deflection. But again, I will repeat it. It's important that if you use required or provided reinforcement, you need to first be sure whether you would like to design the RIPs to completely transfer the loading. For instance, for this case, when I assume initially one way bearing, or you would like to calculate codependent deflection or the reinforcement also for the slab and for the part of the slab as a RIP. Yeah. Okay, so now I'm a little bit over time, but we are almost at the end. So I would like to now just run a quick survey, because we would like to get the feedback in which area of the reinforcement design on RIPs we can improve. Yeah? So there are several options. Variable effective width along the RIP length. It's about to overcome the story when, for instance, we have continuous RIP. We want to design it as a continuous RIP, but we actually cannot because of this limitation. It's also important to mention that for now we do not support the verification of the shear between the web and the flanges, which is required by the code. Also, we do not support the different concrete material or different time of concrete cast between the slab and the RIP. Or we can extend the reinforcement design templates to, for instance, support also input of reinforcement the low reinforcement within the slab, or concentrate the up reinforcement into the web, while there will be also up reinforcement in the flanges, etc. Or also do not support, for instance, non-symmetric T section. You can input the symmetric section for the design, but probably it's not always ideal. Or we can even go a little bit in different direction to enable input of user reinforcement on integration member and actually extend the integration member to be able to cover all the aspects which are supported by the concrete rib. And because you can see that for integration member we have some limitations, like that reinforcement from the integration member is not considered in codependent deflection calculation, etc. So now I will run the poll, and I will be very glad that you will participate. Okay, so now I see that you started voting, so big thanks for that. And after this poll, I will display the results, and it will be end of this webinar. So big thanks for your participation. I hope it will be useful for you. And after the webinar, there will be short survey also, which you can fill. And if you want, we can even contact you later and explain some details if you would have some more questions. Yeah. Okay. So majority of you already voted. So I'm closing the poll and share the results. And you can see that actually results are very interesting. So variable effective width along the rib length, verification of shear between web and flanges, two most demanded, but also extension of reinforcement design templates and user reinforcement on integration member is something what you would appreciate it. Okay, so thank you, and basically that's it from today's webinar. Thank you for participation, and if you would have any questions or feedback, do not hesitate to contact our support or my colleagues or me. We will be more than happy to help you. So thank you, and see you next time. Bye for now.